the gradient function or derivative of fx. Now, if I have an equation y equals fx, or I can say y is fx, we can say y is a function in x. So if I take a point P and I say that point is x, then I can find a y value, whatever this equation was called. I can substitute the x value, whatever this x is, into my equation to find out what y is. So this will be fx. If I now have a second point, and the second point is, let's say, over here, and we call that point Q, and I'm going to say that let's move this x a distance h away from x. Then this will be that distance x plus that h. So this will be x plus h, which means to find what is the y value there will be the function of whatever this value is, which is x plus h. That will give me the two values. If I now want to know what is the gradient between those 2 points, now this line here will be called the second, and we can say that the gradient of that line, equals the gradient m equals y2 minus y1 over x2 minus x1. So if this is y2, this will give us fx plus h minus fx divided by x2, and x2 equals x plus h minus x, which will equal then this x minus x cancel. This will give us fx plus h minus fx divided by h. I can use that formula to find what the gradient of that line. If you can remember from year 11, we said that that will give us the average gradient, the average rate of change, because between the 2 points the gradient changes. So the gradient of the line of the function changes along here. But if I have a straight line between the two, that will give us the average gradient between the two. If I don't want the average, but I want the actual gradient, I want a gradient of the tangent, which means the line touching this point. So I want the gradient of the tangent at that point. What I'm going to do is I'm going to use the same formula. But I'm going to bring this Q closer and closer and closer. So that line, that red line there, with P fixed, I'm going to bring this closer and closer and closer and closer so I can get to that. So what's happening? As I come closer, as this point comes closer and closer, h is going to get smaller and smaller and smaller. If that is the tangent at point P, h will equal 0. However, this will cause us a problem, because if h is 0, I can't use this because I'm not allowed to divide by 0. So I can't use this. But we then learned that we actually can do something. We can say that the gradient of that point is the limit where h strives to 0 of the function. Now, everything else stays the same. So that will be fx plus h minus fx over h. And we said that this is differentiation from first principle. So we said this is differentiation from first principle. And there will be examples of how to do it. But that's the whole thing of writing it. Now, what I can say is that this gradient, just to make sure, that this gradient, the derivative that m equals, and to show that the derivative is, we're going to say is the derivative. So that's one way of doing it. The other one is to say the change in y over the change in x. Now that change, you must have seen this in science before, is dy. That's a symbol for delta. So the change in is delta y over delta x, and because of that it becomes dy dx. The change in y over the change in x. The change in y over the change in x. So that is called the gradient function or the derivative. And if you talk about that, it is at a point, so it's the gradient at a point of any equation. We can use this limit where h tries to 0 of fx plus h minus fx divided by h. You're only going to use this when they say use differentiation from first principle.